Hello, I'm Sebastian. Welcome to 9 Trees podcast. Today, I will summarize and review the book. An Introduction to Statistical Learning, with Applications in R by Gareth James, is a widely used, practice-oriented guide to modern statistical learning, designed for readers who want to understand how predictive models work and how to apply them responsibly. Positioned between theory-heavy texts and tool-only manuals, it explains core ideas like bias-variance trade-offs, overfitting, and model assessment in an accessible way while still treating the subject with scientific rigor. The book is structured around the most common supervised and unsupervised methods used in data analysis, including linear models, classification techniques, tree-based methods, support vector machines, and clustering. Throughout, the emphasis is on interpreting results, choosing methods that match the question, and validating models using sound resampling strategies. A major strength is its hands-on orientation. The R ecosystem is used to demonstrate workflows that a student, analyst, or researcher can reproduce. For many learners, this book serves as a first serious bridge from introductory statistics to real-world machine learning practice. I will give you key takeaways from this book. Firstly, from data to prediction, foundational ideas, and the bias-variance lens, the book begins by grounding statistical learning in the practical goal of predicting an outcome from a set of inputs, while clarifying the difference between inference and prediction. It frames learning problems using concepts such as training error versus test error, and shows why the best-fitting model on past data is not automatically the best model for future data. Central to this discussion is the bias-variance trade-off, presented as a way to understand why flexible methods can overfit and why simple methods can overfit. The reader learns to think in terms of generalization, performance on unseen data, not just a high-end sample score. The book also connects these ideas to interpretability, explaining when a transparent model may be preferable to a more complex black box, even if accuracy is slightly lower. Practical modeling decisions are motivated by the nature of the signal, the amount of noise, and the size and structure of the dataset. This foundation helps readers evaluate algorithms as families of assumptions and tuning choices rather than as isolated recipes, preparing them to select methods that balance accuracy, stability, and interpretability for the problem at hand. Secondly, linear models and extensions, regression, classification, and regularization. A major portion of the text develops linear methods as a baseline that remains surprisingly powerful in real applications. For regression, the book explains simple and multiple linear regression, diagnostics, and interpretation of coefficients, emphasizing when the model assumptions are reasonable and when they are not. For classification, logistic regression and related approaches are introduced to connect probabilistic modeling with decision boundaries and performance metrics. The discussion then expands to methods that extend linear modeling capacity without abandoning its structure, such as polynomial terms, interactions, and spline-style ideas. Importantly, the book highlights the challenge of many predictors and correlated features, where ordinary least squares can become unstable. Regularization methods like ridge regression and the lasso are used to address this issue by shrinking coefficients and, in the lasso case, performing variable selection. The reader is guided to understand how tuning parameters control complexity and how to pick them with resampling. In practice, these chapters teach a dependable workflow, start with interpretable linear baselines, assess fit and generalization, then add flexibility or regularization in measured steps based on evidence rather than intuition. Thirdly, model assessment and resampling, cross-validation, bootstrap, and honest evaluation. The book places strong emphasis on evaluating models correctly, since many modeling failures come from overly optimistic performance estimates. It explains why a single train test split can be noisy, especially with limited data, and introduces cross-validation as a more reliable approach to estimate test error and compare methods. Variants such as k-fold cross-validation and leave-one-out cross-validation are presented in a way that highlights their trade-offs in bias, variance, and computation time. The bootstrap is also introduced as a general resampling tool for quantifying uncertainty and estimating quantities that may be hard to derive analytically. A key lesson is that resampling is not only for scoring models, but also for choosing tuning parameters, selecting features, and deciding between competing modeling approaches. The text encourages discipline separation between model building and model evaluation to reduce leakage and selection bias. By learning these evaluation habits, readers gain practical defenses against overfitting, especially when trying many models or when using flexible algorithms. This topic equips readers with a mindset of rigorous validation that transfers to any software, dataset, or industry setting. Fourthly, nonlinear and tree-based methods, capturing complex structure with interpretability options. To move beyond linear boundaries, the book surveys nonlinear methods that can adapt to complex relationships between predictors and outcomes. It introduces approaches like generalized additive ideas and then focuses heavily on tree-based methods, which are attractive because they can model interactions and nonlinearities automatically. Decision trees are explained as a sequence of splits that produce simple, human-readable rules, along with the downside that single trees can be unstable and prone to overfitting. This motivates ensemble methods that improve accuracy and stability by combining many trees. Bagging and random forests are used to show how averaging multiple trees reduces variance, and variable importance concepts help interpret what the ensemble is using to make predictions. Boosting is presented as another way to build strong predictors by combining many weak learners in a staged process, often achieving high accuracy with careful tuning. Throughout, the book emphasizes the role of tuning choices such as tree depth and learning rate, and ties these choices back to the bias-variance framework and cross-validation. The result is a practical understanding of when tree-based models are preferable and how to deploy them thoughtfully rather than treating them as magic. Lastly, unsupervised learning and dimension reduction, structure discovery, and compact representations. In addition to predicting labeled outcomes, the book introduces methods for learning structure from unlabeled data, a common need in exploratory analysis. It covers clustering approaches that group observations by similarity and highlights how choices like distance metrics, scaling, and the number of clusters can dramatically change results. Readers learn to interpret clusters cautiously, treating them as hypotheses about structure rather than definitive categories. Dimension reduction is presented as a complementary tool for summarizing high-dimensional datasets and visualizing patterns. Principal component analysis is used to explain how new features can be constructed to capture the dominant sources of variation, enabling simpler models and clearer plots. The book also connects dimension reduction to supervised tasks by discussing how reducing noise and collinearity can sometimes improve predictive performance, especially when combined with regularization or when predictors are numerous. Practical considerations are emphasized, including preprocessing, centering and scaling, and the interpretability trade-off when replacing original variables with components. By covering unsupervised learning alongside supervised methods, the text helps readers see statistical learning as a unified toolkit. Sometimes the goal is prediction, sometimes explanation, and sometimes discovering structure that guides subsequent modeling or decision-making. In conclusion, this book is well-suited for advanced undergraduates, graduate students, and working analysts who know basic statistics and want a clear path into modern machine learning without getting lost in heavy mathematical abstraction. It is also valuable for researchers in fields like biology, economics, psychology, and the social sciences who need dependable modeling tools and evaluation habits. The main benefit to a reader's life is practical competence. You learn how to frame questions, choose appropriate methods, and test models honestly. So results are more trustworthy and decisions are less driven by misleading patterns. The focus on bias-variance thinking and resampling encourages a disciplined mindset that reduces costly mistakes such as overfitting and misinterpreting performance. Compared to similar books, it stands out for balancing intuition, methodology, and application. It does not assume deep prerequisites, yet it still explains why methods work and how their tuning affects outcomes. The integration with R workflows helps readers move quickly from concept to implementation, making it a worthwhile purchase for anyone who wants a single, coherent guide that supports both learning and real project work. If you would like to support Gareth James, you can buy the book through the Amazon link I've provided in the podcast description. After reading the book, please let me know what you think and share your thoughts. See you around.